Hello, everyone. Thanks for coming to Nemotron Summit. My name is Dan Su. I'm a senior research scientist from the Nemotron Pretraining team. Today, I will take you inside Nemotron and share the key techniques for efficient and reproducible foundation model pretraining. So currently, the availability to foundation models is changing quickly. Large language models such as like Q1, DeepSeek, Llama are available to researchers and developers, so which fosters many innovations in AI. However, on the other side, like the pre-training side, the pre-training details of how those models are pre-trained are very, there are very little information has been shared. And we believe that by open source, our pre-training data and our data recipes could help like the user to better understand the model capabilities and also will help speed up the development of the field. And also efficiency is quite important, just as Brian mentioned. Like we have designed sophisticated architectures to maintain like higher throughput during inference and still maintaining state-of-the-art performance. And we also have model compression techniques specifically designed. So in this talk, I will cover like three major things. First, about how we curate high-quality pre-training data and what is our data mixture strategy. And second, I will go through our model architecture quickly. And third, I will also mention about our model compression techniques. Yeah, so Brian just mentioned about our Nemotron Nano V3 model, right? So I will very quickly pass this. Basically, Nano V3, it has state-of-the-art performance compared to the other models like Q13, as you can see, right? We have better performance at MMU Pro, at code, at math, and we have on-par performance at MMU and common sense understanding. And it's not only about accuracy, right? Like from the left figure or right figure, you can see Nano V3 has like, here in this figure, it has lower, like 4 times lower KV plus SM cache, which is an indicator of inference speed. So basically, we have higher throughput. So basically, yeah, it's a very good model. And I believe you guys will be curious about our techniques. Yeah, now let's start. So here is a very rough like overview of our pre-training workflow. It consists of like 3 pillars about the data and architecture and the model compression. So from the data part, you can see we have a very rich pre-training data sources such as Common Crawl, which is our web data source, and like GitHub for code and math, etc. And we have like sophisticated data curation pipeline to process the data, and we also have SDG pipelines. And architecture, we have evolved from the very beginning. It's like the traditional dense transformer architecture to the middle one, which we use like hybrid transformer models, and to the most one that we use in Nano V3, which is a hybrid MOE architectures. Yeah, and we also have like state-of-the-art model compression techniques. So now let's check out about the pre-training data. So in terms of a pre-training data challenge, like there are 2 major challenges I summarize here. Like first, very limited availability of large-scale open source pre-training data sets. And second, absence of detailed, reproducible like data curation and SDG recipes. So in this figure, it's the AA openness index, like Brian just mentioned it, right? They released this index this morning. So this is a breakdown of that index. Basically, the x-axis measures the model's transparency, and the y-axis measures the model's availability. So as you can see, like in the top right part, the green part, like 2 models are there. That means that they have like high model transparency. One is OMO 3, and another one is Nemotron Nano V2. Like OMO 3 was pre-trained over like around 5.9 trillion tokens, and the Nemotron Nano V2 we were pre-trained over 20 trillion tokens. That's the first difference. Second, if you compare the model's performance, if you check out their tech report, Nemotron Nano V2 performs much better than OMO 3 at almost every aspect. Yeah, so we believe our data is also like higher quality. Yeah. So now let's check out the pre-training data we have open sourced. Overall, we have open sourced around 6.7 trillion training tokens already to the community. And here is a breakdown. So Nemotron-CC is the one of the largest open source English web text-based pre-training data sets. And Nemotron-CC-Math, as Brian just also mentioned, it's a specialized math pre-training data sets. And we also open source the pre-training data sets for code and also for SFT. And we also open source our synthetic data. Yeah, I will go through some of them like in the next slides. And we are not just stopped here. There are more like open source data coming soon. For example, Nemotron-CC-Math 2.1 and Code V2 and Pretraining Code V2, etc. That has been used in the Nano V3 pretraining. Yeah, so let's go through. Nemotron-CC basically is one of the largest open source English Common Core-based pretraining data. So you can compare with previously one like DCLM and FanWeb here. You can see we are not better at, like we have more unique tokens, and we also include some synthetic data here. So both of these could benefit longer horizon pretraining. And if you compare the performance, you can see from the figure here, basically Nemotron-CC high quality subset outperforms the previous best one, which is DCLM, with like 5.6 MMU improvement, and we have more tokens. And here is like how we built Nemotron-CC. But I mean, I'm not going to go through each of them, but like the takeaway is like you can see we have a sophisticated SDG pipeline. Yeah, it's not easy to build high quality data. And I just want to talk about two major parts of this pipeline. One is the model-based quality labeling part, and another one is the SDG part. Yeah, so for model-based quality labeling, we design like still a little bit sophisticated pipeline. So instead of just using one quality classifiers to like give the quality label, we employ like multiple different quality classifiers because we believe by assembling them, each of them may give you a different perspective of high quality. So by assembling them, you may get more high quality data. And we assemble the score and we map them into the final quality label. And the final quality label is more correlated with downstream task performance. And for SDG, we also like design it like strategically. So for low quality data, we did not just like get rid of them or remove them. We still try to like improve their quality. So we design some kind of like, for example, rewriting a prompt, try to rewrite and improve the quality of low quality data. And for high quality data, the goal is try to increase the diversity. So that's why we designed different style of prompts and to like try to convert the original raw text into different style or formats to increase the diversity. And yeah, that's for Nemotron-CC. And for Nemotron-CC-Math, as I mentioned, it's one of the best state-of-the-art open source pre-training data sets on math. So it outperforms the previous best ones such as the Open Web Math, FanMath, or Mega-Math. So we have two subsets. First one is a 4+1, and second one is a 3+1. So both of them has like more tokens, and both of them perform better than the other data sets. You can check out like the red part, bar chart comparison. The dark green is our model's number, and compared to the previous one, you can see we excel and better at knowledge, code, and math. Yeah. And here I just show one concrete example. So the original data, you can see it contains like many equations, formulas, right? It's not easy to pass. So Open Web Math and Mega Math Web, they failed to pass those equations or formulas correctly. But our like Nemotron-CC can preserve those equations quite well and in a structured way. So that's a success, like why we excel at like math capability. And we just see, right, data curation is not easy, it's complicated. That's why we also have like SDG work. So here I just want to share this MAND Nemotron work. MAND represents for like math-informed synthetic dialogues. So basically we kind of generate the dialogue conversations from the high-quality math text. So you may ask like why in a conversational way. Basically, the idea or the motivation is like we want to expand the original context by using conversations step by step. So in the conversation, each participants will add some extra information or explanations to the context. So that's the motivation. And in this work, we explore like different conversational scenarios. For example, a teacher talk to a student, or a professor talk to another professor, layman talk to a know-all person, such as, and we found out like, basically if the knowledge gap between these two personas are larger, and the quality you generated will be better, like, by downstream task performance. Yeah, that's a takeaway. And you can check out the details by scanning the QR code and check out the original paper. And yeah, you see like we have a lot of data, right? We not just like throw them together into like model pre-training using their natural distribution. Instead, we need to design like sophisticated data mixture and ordering ways. So here we illustrate the Nemotron Nano V3 base data mixture and ordering. As you can see, we have a 3-phase in pre-training, and at each phase, you can see we have different data mixture. And for example, at phase 1, you can see we include a broader set of data because we want the model to learn as much as possible. And at phase 2 and phase 3, we have more focused. So we focus more on high quality data or like domain data, like code and math. And on phase 3, we even switch like larger. Yeah, and in this table, I just show like what we did for multilingual data. For example, you see on the data mixture part, like we have 5% of multilingual, right? But inside the multilingual category, there are different multilingual data sources. Like here we have 4 different sources. You still need to assign some weights to the different sources. So we still conduct ablation studies, like to evaluate their downstream types performance, to decide their quality and assign the weights. And yeah, I just talk about the pre-training data. And this work I also want to share. This is a very recent work and very innovative work. It's called ILP, Reinforcement as a Pre-training Objective. So basically, this work, use IL for reasoning. It like reframes IL for reasoning into the pre-training objective. So it bridges the gap between next token prediction with chain of thought reasonings. Yeah, the key idea between this is like we want to treat the chain of thought trees as an action exploration. And the reward will be decided by like whether these COT trees can help the next token prediction. So as you can see from the bottom left, so the reward is calculated by the 2 differences between this probability. One is using these COT trees, one is without. So the reward will be positive only if these COT trees will help the next token prediction. Yeah, and on the top left, we show the results. So it's a two scenario comparison. So like we compare the base model and versus base plus ILP, and we also compare whether these improvements can be sustainable after post-training. So as you can see, like on the 2 scenarios, the reasoning capabilities of like with ILP has been improved. So you can scan the QR code and check out the original paper. This is a very interesting paper. Yeah. Here I summarize the pre-training data, like relevant details. So we have released the model and also the data on Hugging Face. We also have a lot of published papers. And we also have data curation platforms like Nemo Curated and also SDD platforms such as Nemo Skills and Nemo Data Designer has been shared. Yeah, now let's check out about the model architecture. So at the very beginning, for our Nemotron-4, we are using the transformer architecture. So basically, it's multiple layers of the transformer block, and within each block, it's like a self-attention layer with FFN layer. So for self-attention layer, it's good because it can process the sequence in parallel, right? But the drawbacks is also very obvious, yeah, because during training or inference, like the computation will scale like quadratically with sequence length. So if you check out like this figure, this is the KV plus SM cache. So it will increase linearly with the sequence length. So to overcome that limitation of self-attention, my colleagues designed this hybrid Mamba-Transformer architecture. So basically, they replace most of the self-attention layer with Mamba-2 layer. So the benefits of Mamba-2 layer is like it's a recurrent state space model. It has a fixed KV cache, so it will not increase when you increase the sequence length. So it will give you reduced memory requirements and faster generation on long sequences. So if you compare in this figure, we show like the red curve is our Nemotron Nano V3, which we use a hybrid transformer architecture. It has like 5 times more, like less KV plus SM cache compared to our like Nemotron-4. And we also accuracy is also what we care about, right? So we conducted apple-to-apple comparison. So we train like 2 models. One is hybrid, one is dense transformer. Both of them with 8 billion parameters and using like 15T tokens. So basically, this is quite large scale. And we compare on MMU math, code, and reasoning. And here, like the blue line is our hybrid model, and the green line is the transformer model. As you can see, like dense transformer model. So as you can see, basically the hybrid architecture can match the performance of the dense transformer, and even sometimes it can outperform. So we continue train a larger model, which is the Nemotron-H 56B with 20 trillions, using this hybrid Mamba-Transformer architecture, and we compare our model's performance with the other state-of-art, such as Llama 3.170B and Q1 2.572B, and even Llama 3.145B. Yeah, as you can see, our Nemotron-H 56B achieves state-of-art performance. Yeah, and of course, we have like higher throughput. So this proves that the hybrid architecture can can scale quite well. And then we released the Nano V3, which is one of the first open source state-of-the-art hybrid model. So as you can see, in terms of accuracy, we are better than Q138B at almost every aspect. And in terms of the inference speed, we also have like 3 to 6 times higher throughput than Q1 model. And built on the successful of hybrid model architecture, we evolved to the most recent successful one, which is the hybrid Mamba-Transformer MOE architecture. So basically, and this one was using Nano V3. And basically, we replace FFN layers in Nemotron-H with mixture of experts. Then you may ask, why MOE? The answer is very obvious, right? Like it can give you like similar accuracy, but still give you with like 3 to 4 times fewer active parameters, which can translate directly to training and inference lobs. Yeah, if you check out the figure on the bottom right, you see the green line is the Nemotron Nano V3. It can reduce like further 4 times like KV plus SM cache compared to Nano V2. Yeah, so this is great. And now, okay, let's come to the model compression part. So we use Minitron to do the model compression. So basically, 2 major steps, pruning and knowledge distillation. So for pruning, like first you train a teacher model, fully trained teacher model. Then the second step is we estimate the importance inside of each of the layers. For example, you estimate the importance of the embedding dimensions or the attention heads, such as that. And then you rank them from the most important to the least important, then you trim them. So you will have a student model. But a student model, normally it has less parameter, but still a little bit like downgrade performance. So you still need some distillation to recover the performance. So that's the main idea. So we apply Minitron and compress the Nano V2 12B to the 9B base. And you've already seen this figure already, right? So Nano V2 9B has like very good performance. Like this will prove that successful Minitron's techniques. Yeah, okay, that's all for my sharing. I hope you can get some like ideas and know more about our techniques. Yeah, and for those who attend NeurIPS, there are also 2 relevant talks. The first one is Nemotron Clam, which is basically it's about data mixing, bootstrapping for smaller language models. And Minitron is about our model compression. So you can go to those sessions to learn more. Yeah, that's all. Thank you. Thank you so much.
Thank you, Dan-Su. Are there any questions for Dan-Su?
So I was wondering if the Nemotron pre-training uses any distillation from like frontier models, because I know that Olmo from the Allen Institute does not, to make sure that their data sets are able to be publicized. I was wondering if you knew that.
Oh yeah, we have like synthetic data in our pre-training data set, right? So those synthetic data, we use like some open source model like Q1 or DeepSeek, which is legally approved. So yeah, that's why we can release our data.
Okay,
yeah.
Thank you.
Yeah.
Hi. For those data curated by language models, how do you verify the correctness of the answers?
Oh yeah, we do have different like ways. For example, like for some kind of, if you are doing like, for example, multiple choice ways, right? We can use, you can generate multiple answers, and you can use majority voting, for example, to treat them as a correct answer. Yeah, that's one way. Of course, you can also employ a language model to, maybe a stronger language model to give you, to judge whether this is correct or not. That's another way. Yeah, yeah, that's a high level answer.
Any other questions?
Hi.
Hi.
Could you talk more about how you do the weighting for based on the quality?
Actually, yeah, first of all, like, we do have papers talking about like the details about the data mixture and ordering, yeah. And generally here the answer is like, first we need to further categorize our data like into smaller categories. For example, for crowd data, for example, we further split into like crowd medium high, crowd synthetic high, etc. And we conducted ablation studies to test their performance. For example, for multilingual data, like we have subsets, right? We test their downstream task performance, and the diverse QA cross subset performs the best, then we will assign some weights. Yeah, something like that. Yeah, in that way, iterative way. So you can imagine there will be very extensive ablation studies. Yeah.
Hi, can I ask how you evaluate the importance for different embedding for the last phase, the pruning and the distillation?
Yeah, that's a good question. Actually, I cannot give you a direct answer because I'm not doing the model compression. So I suggest you, maybe you can go to the Minitron session and to know more about it. Yeah, sorry.
We have one more question over here.
Hi, thank you for the great talk. I have a question about like how, what is the accuracy of your hybrid transformer structure on like very long context tasks?
Oh yeah, actually, I didn't show it here, but we do have like, yeah, actually for our long context, first of all, it has already maintained all the performance here. That's for first thing, but we didn't show the long context performance. And they also have like SOTA, like score on ruler, those kind of benchmarks. Yeah.
Okay, what about like long context such as like 1 million tokens, like on like needles in the haystack or even like more difficult tasks?
Sorry, what's
like if the sequence length is like over a million tokens, like since you have like a fixed KV cache and it's like using fewer KV cache, how would the model perform if like the context length is like over a million tokens?
So far our context length it's not like 1 million yet. So yeah, I think we can talk about details like offline. Yeah.
Okay.
I can connect you to our like expert at long context. Yeah.
Yeah. For question on compression, please feel free to come after the session and chat about that. Yeah, about Minitron.
Yeah, Minitron. Yes.
All right, do we have any more questions? All right, thank you, Dan. All right, while Oleski Kuchayev is getting set up for our next talk, I'm going to do the next raffle. This is another $500 in Brev credits. For those that came in late, I'm going to add yours in now.